So my name is Aram Manaselian. I am from Calculus Algebra team of Wolfram Research. And today I want to speak about symbolic solutions of differential equations. As we know, we have two main functions for solving differential equations in Wolfram language, DSolve and NDSolve. They both do the same job, but in a different way. NDSolve solves differential equations numerically, so its outcome is interpolating function. And we have to provide also initial conditions or boundary conditions for NDSolve, and all the parameters in the equation must be numerically. In contrast to that, DSolve solves differential equations symbolically, so its outcome is an analytical expression. And we can also solve differential equation without initial or boundary conditions, and we can keep also non-numerical symbolic parameters in the equations. Of course, NDSolve is more powerful and can solve more differential equations than DSolve, but the results obtained by DSolve are more general, easier to understand, and easier to use. That is why we're always working hard to improve DSolve functionality, to add new features and also new types of differential equations, which can be solved by DSolve. And today I want to speak about recent progresses in this area. So my talk will be organized as follows. At first, I will speak about singular solutions for nonlinear differential equations, and will demonstrate how we can find such solutions using DSolve. Next, I will speak about the improved method of undetermined coefficients, which will allow us to find fast and simple solutions for inhomogeneous linear differential equations with constant coefficients. And next part of my talk will be about new type of differential equations, about fractional differential equations, which can be solved now by DSolve. And at the end, I will demonstrate the updated documentation pages and tutorials related to symbolic solutions of differential equations. So let's start from singular solutions. As we know, the general solution of any differential equation contains arbitrary constant parameters, C1, C2, etc. But for some cases of nonlinear differential equations, there can be also some so-called singular solutions, which cannot be obtained from the general solution by choosing some specific values of arbitrary constant parameters. To illustrate this, let's consider following Galois equation. The solution of this Galois equation is a linear function, xc1 minus c1 squared. So now we can plot the family of these solutions for various values of parameter c1. And as you can see from this figure, this family of lines has an envelope function here, which is a parabolic function. And this parabolic function is also a solution for the differential equation. But we cannot obtain that solution from the general solution because each point of this solution belongs to different lines of the general solution. And this is the singular solution of this differential equation. And I want to say that the first bug report that DSolve missing this kind of singular solutions have been reported many years ago in 1997, I think. And after that, also we get several bug reports about this issue, and also some discussions in Mathematica Stack Exchange. And finally, in version 14.1, we have implemented support for singular solutions in DSolve. So now if you want to get a singular solution from this Galois equation, we can use a new DSolve option with name IncludeSingularSolutions true. And with this option, DSolve starts to search also for singular solutions and will present them together with the general solution. So as we can see in this case, the singular solution is x squared divided by 4. And we can easily verify that this solution is correct. And here is another example. Let's try to solve following logistic equation. This is the general solution of the equation, and it's again contained with constant parameter C1. Again, we can plot the family of these solutions for various values of the parameter C1. And as you can see here, we have two envelopes, or we can say two equilibrium singular solutions, y equal to 0 and y equal to 1. And again, with option include singular solutions true, we will get both singular solutions together with the general solution. Now, let's speak about inhomogeneous linear differential equations. As we know, the general solution of linear inhomogeneous differential equation consists of two parts: general solution of homogeneous equation and particular solution of inhomogeneous equation. And usually, DSolve uses the method of variation of parameters to find the particular solution for linear inhomogeneous differential equation. And here's an example. We have a second order differential equation with inhomogeneous term x squared. And this is the general solution of this equation. Here, the first two terms are the general solution of homogeneous equation, and this last term is the particular solution for inhomogeneous equation obtained using the method of variation of parameters. But the method of variation of parameters uses Wronskians of the general solution of homogeneous equation, and also calculates several integrals containing Wronskian and inhomogeneous term. And in cases, if the inhomogeneous term has more complicated forms, or the general solution is more complicated, we can get huge expressions from the method of variation of parameters, and in some cases, even unusable expressions as a solution for inhomogeneous equation. That is why we are always trying to implement some new methods which allow us to avoid using method of variation of parameters for some cases. And one of that methods is the method of undetermined coefficients. The method of undetermined coefficient can be used for solving inhomogeneous linear differential equation constant coefficients if the inhomogeneous term is a polynomial function of independent variable. For example, let's consider this example. We have a second order differential equation with this type of inhomogeneous term. This equation can be easily solved with the method of undetermined coefficient. We just search the solution, particular solution, as a polynomial function with undetermined coefficients, substitute that solution into the equation. As a result, we will get a system of linear non-differential equations to determine the unknown coefficients of the particular solution. So we will avoid integrations and Wronskians, and we will get just simple polynomial expression as a particular solution. And in version 13.2, we have significantly updated and improved this method of undetermined coefficients. So now it can work also with more complicated inhomogeneous terms of following form: px exponential function ax cosine bx plus qx exponential function ax sine bx. Here a and b are any constant coefficients, and px and qx are polynomial functions of x. And here is an example which can be solved with this improved method of undetermined coefficients. We have a first order differential equation here, and this is the inhomogeneous term. And here is the solution obtained by this new method in version 14.2. And if we compare the solution of the same equation obtained by version 14.1, you will see that the solution is much more complicated and very large. So again, it is solved with method of variation of parameters, but solution is not good enough. And now we have a good improvement. And here is another example of higher order differential equation. We have fourth order differential equation, and this is the inhomogeneous term of it. And in this case, the general solution of homogeneous equation contains root objects, because the characteristic equation of the homogeneous equation cannot be solved analytically. But as you can see, the particular solution is free from that root objects, and it's very simple. And if you compare the solution of this equation obtained in version 14.1, you will see that the leaf count is more than 2000. So the solution will be huge and almost unusable. And I want to say that the improved method of undetermined coefficients can be used also for solving systems of inhomogeneous linear differential equations. Here is a simple example of a system of two equations. M is the coefficient matrix of the system, and G is the vector of inhomogeneous terms. And we can solve this system using vector variables. And this is the solution of the system. The leaf count of the solution in version 13.2 is 258. And if we solve the same equation in version 13.1, it will be more than 800. So even for this simple system, we have 3 times improvement. Now let's speak about fractional differential equations, new type of differential equations, which can be solved now by DSolve. Since in version 13.1, we have implemented fractional derivatives and also fractional Laplace transform, it was obvious for us that the next step must be implementation of fractional differential equations, which we also did. Fractional differential equations are differential equations which contain at least one fractional order derivative of the form d alpha dx alpha, where alpha can be any real positive number, not necessarily integer. So we can say that fractional differential equations are generalizations of the ordinary differential equations. As Tigran taught in his talk, in version 14.1, we have implemented 2 definitions of fractional derivatives, Riemann-Liouville definition, fractional d, and Caputo definition, Caputo d. But currently, DSolve can work only with Caputo type fractional differential equations. This is because Caputo derivative is more similar to integer order derivatives. For example, a Caputo derivative of constant is always 0, but Riemann-Liouville derivative of constant is not 0. Also, for Caputo type differential equations, we can solve initial value problems of fractional differential equations, and the initial conditions can be given only for integer order derivatives of the unknown function. And I want to say that currently any Caputo type linear fractional differential equation with constant coefficients can be solved in Wolfram language. And here is an example of Caputo type fractional differential equation of order 9/10. We can solve this equation using Laplace transform method. At first, we can calculate the Laplace transform of the equation. And if the equation is linear with constant coefficients, the Laplace transform will be a non-differential algebraic equation, which can be easily solved. As a result, we will get an expression for Laplace transform of the unknown function y of t, this expression. And next, as a next step, we can use inverse Laplace transform to find the solution of the fractional differential equation. And as you can see, the solution is a Mittag-Leffler E function. The Mittag-Leffler E function is the most important function in fractional calculus because it plays the same role as exponential function in integer order calculus, which means that any linear fractional differential equation with constant coefficients can be solved in terms of Mittag-Leffler E functions. And starting from version 13.1, we can solve this type of equations directly using DSolve. And we can do that in the same way we solve integer order differential equations. We just write DSolve, equation, comma, dependent variable, comma, independent variable, and that's it. This is the same solution obtained by DSolve. And we can easily verify that this solution is correct by substituting it into equation and doing full simplify. And as I said, we can solve also initial value problems for Caputo type fractional differential equations, and all initial conditions can be given for integer order derivatives of unknown function. And the number of initial conditions depends of the order of fractional differential equation alpha, and will be equal to scaling of alpha. So as an example, let's try to solve a fractional differential equation of order pi with initial conditions. This example also demonstrates that the order of differential equation can be any real number, even non-rational number, such as pi. This is the equation. And since the order of equation is equal to pi, which is more than 3 and less than 4, we will need 4 initial conditions here. For function itself, first derivative, second derivative, and third derivative. And this is the solution of initial value problem. And here is the plot. In version 13.1, we also can solve some simple systems of fractional differential equations, but here we have some limitations. All equations must have same order alpha less than 1. Here is an example of two fractional differential equations with order 16, 17. As you can see, the order is close to 1. And if you put the order equal to 1, this system has a nice solution, xt equal to cosine t and y of t equal to sine t. But for this fractional order, we will get solution expressed by Mittag-Leffler functions. And we can plot the solution, and you can see that the solution have some similarities with cosine and sine functions. Of course, now the solutions are non-periodic, but still oscillatory. And the parametric plot of the solutions will be a spiral, as presented here. Also, I have to say that in version 13.2, we have implemented also asymptotic series solutions for fractional differential equations using AsymptoticDSolveValue function. As an example, let's solve a fractional differential equation of order 0.7. We can solve it using AsymptoticDSolveValue, and here's the solution with approximation order equal to 5. And since this equation is with constant coefficients, we can also solve it exactly using DSolve or DSolveValue. So this is the exact solution expressed by Mittag-Leffler function. And we can compare the asymptotic solutions for different approximation orders with the exact solution. Here is the comparison. This blue line here is the exact solution, and other curves demonstrate asymptotic series solutions for different approximation orders, 5, 10, 15, 20, etc. But the main advantage of AsymptoticDSolveValue that it can be used also for solving fractional differential equations with non-constant coefficients. For example, let's try to solve following equation. It's a fractional differential equation of order 3-second, but with non-constant coefficients. We have x here, and DSolve cannot solve this type of equations yet, but we can easily solve it using AsymptoticDSolveValue, and this is the solution, series solution for approximation order equal to 15. Now, next important question, why we need these fractional differential equations, and have they any practical applications? And the answer of this question, yes, they have. Actually, the fractional differential equations has a long history, but recently they became very popular because of many applications in different areas of science, such as physics, chemistry, engineering, economy, etc. And here I will demonstrate a few simple application examples of fractional differential equations. And the first example is fractional harmonic oscillator. As we know, the equation of harmonic oscillator is a second order differential equation. So what will happen if we replace the order of equation from 2 to 1.9? So this is the equation of fractional harmonic oscillator, of course, with some initial conditions. The solution will be a Mittag-Leffler function, and we can plot the solution. And as you can see from this figure, the solution of fractional differential equation behaves like a damped harmonic oscillator. To clarify this issue, let's also solve the equation of damped harmonic oscillator for some unknown damping factor A. So this is the equation of damped harmonic oscillator with same initial conditions. And here is the solution obtained by DSolve or DSolveValue. Now we can fit the data obtained from the solution of fractional harmonic oscillator with the function for the damped harmonic oscillator to determine the corresponding value of damping factor A. We can do that using these two simple lines of code. And here is the result. corresponding value of damping factor is equal to this number, 0.152. And now we can compare the results of fractional harmonic oscillator and damped harmonic oscillator. As you can see, both curves are perfectly sitting on each other, which means that there is a direct connection between order of fractional differential equation and damping factor of the damped harmonic oscillator. And this also means that we can use the order of fractional differential equation to model some complicated systems. And here is a similar example. Let's consider the electrical LC circuit. The equation for current in electrical LC circuit is a second order differential equation. So this is the equation. I just replace second derivative of the current by Caputo derivative here for the alpha. And we can solve this equation using DSolve or DSolveValue. If we put alpha equal to 2, we will get the classical solution with cosine function here. And if we put the order equal to 1.9, we will get the Mittag-Leffler function. And we can again compare the results of classical solution and fractional solution for different values of alpha, which is presented in this plot. And again, as you can see, for fractional equations, we have some damping oscillations, which we can take into account the resistance of the LC circuit by changing the order of differential equation without actually entering resistance into the equation. So this is another application. And final example, which I want to demonstrate here is dynamical system. I found this example from following book by Kilbas et al. With title Theory and Applications of Fractional Differential Equations, published in 2006. So let's consider a thin plate of mass m and area s that is immersed in a fluid with viscosity mu and density rho. And the plate also connected by a fixed point by a spring with spring constant k. And we also have some acting force here. And in the book, the authors have demonstrated that this system can be modeled by a second order differential equation with fractional damping term. Here is that equation. Here A is the liquid parameter and B is a spring parameter. And currently we can solve this differential equation using DSolve. To do that, we have to specify the force. So let's choose a step-like force, which is presented here. And we can give some numerical values to parameters A and B. And after that, we can solve the modeling equation using DSolve, and we can plot the solution. So this is the plot of the solution, which demonstrates the motion of the plate inside the liquid. And in the last part of my talk, I want to speak about documentation, updated documentation pages and tutorials related to symbolic solutions of differential equations. In version 14.2, we have updated the documentation pages related to differential equations such as DSolve, DSolveValue, AsymptoticDSolveValue, etc., and inserted all the new examples and new topics which we added in recent years. For example, let me demonstrate the DSolve documentation page. Here in scope section, you can find a new subsection with named fractional differential equations with many examples in it. And for example, in options section, there is a new subsection about singular solutions. And there are also many new examples covering all new features and improvements which we made in this version. And also I want to demonstrate you the bottom of this page. There is a section with name tutorials, and we have a very nice tutorial here with name symbolic differential equation solving. And if you are a beginner who wants to learn about differential equations, about types of differential equations, about solution methods, I think this is the best place to start, because it's like a textbook with a lot of examples, with very clear discussions, etc. And this tutorial, which was created several years ago, have been completely updated and improved in version 14.2. And now it also covers all new features and improvements which we made in recent years.